right, let's do this. If you hear me type in, once again, I'm just sending out the link to my students, my wonderful, amazing students. We're live. All right, sent. Get this, 2, boom, boom, and boom. All right, so tonight, let's go. Start off a little late, sorry about that. But I think tonight will be, the next 2 days are going to kind of blend together. The next 2 evenings will blend together in the topics we're doing. But tonight I'm focusing on naming and formulas. So determining the name, writing a formula, all that fun stuff, checking your charges, and then properties of compounds. So there's 4 main, I'm going to probably start with properties first and then go into naming. But like I said, it's all going to kind of blend in. It's all going to blend in. So there's 4 main types of compounds that you need to know and be able to recognize. We have ionic, covalent, or molecular. Hush. We got network solids, and everyone's favorite that people love to forget, metallic. Now, naming metallic's pretty easy, and recognizing metallic is also really easy. So I'm going to do that one first. Metallic is metals, and only metals, like a metal. Any metal has metallic bonding. So for example, silver. If you have like a silver ring, pure silver, 100% silver, the only bonds in that silver ring, if it's 100% silver, is a metallic bond. Or K, good old potassium, is a metallic bond. So if you were to look at the periodic table, because you're like, I don't remember the metals, the non-metals, Mr. G, there's so much to learn in chemistry, there's just always stuff to do. I'm going to highlight here in orange, because why not, all the metals. Metals. Technically these are too, but we don't, honestly, we like barely talk about these. So the only metals we're really concerned with are the ones in the main group of the periodic table. So, orange, you glad I didn't say banana? Those are the metals. Red, boop, 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 boop. Sometimes AT's included. I've seen on certain lists where AT's included. But the red are the metalloids. Metal. And then in beautiful blue, my favorite color. Don't forget hydrogen. Blue is the non-metal. All right, so orange is the metals, red are the metalloids, and we'll go into metalloids a bit more when we do periodic table, and blue are the non-metals. Yay! Carbon's included in that, if it wasn't very clear. Non-metals, blue. Okay. So, back to this. Metallic bonding has a metal in it. Makes sense. Metals, high boiling points and very high melting points, and you can always look these up on lovely table S. I wish I made this table better, but that's okay. So, The next big thing to know about metals is they have mobile valence electrons. And I always kind of talk about in this class as metals, they don't really like to hold on to their electrons. They're always looking to give them away. And they have all their valence electrons are on the outside in that outer shell, the last shell, and they're always moving. They're constantly moving all throughout the metal. And it's actually that mobility, these mobile valence electrons, that allows them to have some properties, like they're malleable. So those electrons allow them to be like kind of a shield, so you can hammer them into different shapes. Like you can form it into a ring even, perhaps. And they're ductile, which means you can draw them into wire. You can like stretch them out into a wire. Through the wire. Go Kanye. There was another word I was trying to think of with these valence electrons here. They like to sometimes, I haven't seen it too often, but delocalized. Delocalized, meaning they don't stand still. They move around. They're not local. They're like tourists. They're always moving around. All right? Those are characteristics of your metallic bonds. Those are properties of anything with a metallic bond, which is any pure metal. So if you have a metal, say it has metallic bonding. Network solids are molecular in nature, but they're special. They're special molecular compounds. And there's 4 that you need to know. Diamond, graphite, silicon carbide, and silicon dioxide. Now, while technically all of these contain nonmetals or metalloids in their structure, they do have some interesting properties in the sense that they are very high melting points and very high boiling points, which is uncharacteristic of other molecular compounds. They can't conduct, however. They do not conduct electricity in either the liquid or aqueous or solid or any state of matter. They cannot conduct electricity. Metals, I didn't really highlight this, but I was hoping it would be obvious, are very conductive. So they can conduct heat fairly well, most of them. They can conduct electricity pretty well. The network solids are molecular compounds, which means they're only nonmetals, or they have a metalloid like silicon here. But what differentiates them from the molecular compounds is that they have high melting and boiling points, which is weird from most molecular compounds. So a covalent compound or molecular compound are nonmetals only. So they only contain a nonmetal, which from before, when we highlighted it, is everything in blue. Don't forget hydrogen, but everything in blue. So, because they're only nonmetals, they tend to have low melting points. They tend to have low boiling points. They tend to be poor conductors. Conductors. I can spell. I'm just not very neat. So they have low melting points, low boiling points. They tend to be poor conductors. Examples like H2O, CO2, O2, anything with just nonmetals is a molecular compound. Versus ionic is a metal with at least one other nonmetal. So it's both bonded together. So an ionic compound has ionic bonds, which is a metal and a nonmetal. a positive ion with a negative ion. So, you need to have one of each. So a lot of my students like to say Ag and K and any of these metals over here have ionic bonding. And they do if they're paired with a non-metal. They have to be paired with a non-metal to have ionic bonding. So this tends to mean that these have high boiling and melting points, like the metals, but they only conduct in solution. So ionics only conduct when aqueous, when you dissolve them in water, or as a liquid. Because, and we're going to say this again and again and again, we need these ions to be moving. We need moving charged particles to conduct electricity. And the ions as a solid, when they're in the solid ionic bond, aren't moving. They aren't free to move. But as soon as you take, let's take an example here, NaCl as a solid, and you put it in water, H2O, that thing's going to break apart. And you're going to get a bunch of positive ions and negative ions in solution here. And now that enables it to be conductive. Okay, so NaCl as a solid, when you dissolve it in water, will dissociate into its ions. Ions are charged particles. Look at the review from yesterday if you need help remembering anything dealing with atomic structure. Okay, so properties. I'm trying to think if I'm missing anything. I feel like I am. I don't think so. I guess we can talk about solubility, but that again, that kind of just hits in so many units. So solubility of each of these. Do they dissolve in water? Dissolve in water? Question mark. Ionic? Depends. Most do. Check table F, and we'll worry about that later to see if they don't. Covalent / molecular. I'm going to throw some words at you that we're going to review later. Yes, if polar. So that's like dissolves like. So water is polar. If the other compound is also polar, it will dissolve because of the principle of similar things dissolve in similar things. Network. No. Drop a diamond in water, it's not going to dissolve. That would be strange. In metals, no. So, most of your ionics will. If they don't, it's on table F somewhere. A lot of your moleculars do, as long as they're polar. There's plenty of examples of molecular compounds that are not polar, like oil is not polar. And network and metallic is a no. If you take some aluminum foil and just chuck it in water, it's just going to sink to the bottom or float. Does aluminum float? No, aluminum floats. Either way, you put a metal in water, it's not going to dissolve. All right, so I just wanted to cover some of these properties here. Ionic, metal and a non-metal, high boiling point, high melting point, will conduct in solution, aka when it's been dissolved, or if you melt it down to a liquid. That's a bit harder to do. Ionic compounds, as we just stated above, have high melting points. For ionic compounds to conduct, those ions need to be moving. We need moving charged particles. So when you put an ionic compound in water, like NaCl, it will dissociate into its positive ion, the metal, and its negative ion, the nonmetal. Molecular compounds are only composed of nonmetals. They have low boiling, low melting points, and are always poor conductors no matter what phase. Network solids are a special case of molecular compound. The 4 examples that you need to know are diamond, graphite, silicon carbide, and silicon dioxide, which is sand. They have high melting and high boiling points, but they can't conduct. So those 3, ionic, covalent, and network, are separated by their conductivity and melting and boiling points. Ionic and network both have high melting and high boiling, but network cannot conduct, and ionics can as long as they're dissolved or in liquid form. Molecular compounds are all low and no. Molecular compounds have low melting and boiling points, and no, they cannot conduct. Low and no. Metallic is just a metal, bonded with nothing else but metal. So any metal off the periodic table will have metallic bonding. Boiling, high melting points, they have those mobile, delocalized valence electrons. They are very conductive. They are both malleable, meaning you can hammer them into shapes, and ductile, meaning you can draw them into wire. Naming and formula writing these bad boys. Ionic. There's 2 types of ionic compounds. There's binary and ternary. Bics and ticks. Binary means you have your metal. Why would I use X? You have a metal which is positively charged bonded with a nonmetal which is negatively charged. And there's 1 of each. So there's 1 metal, 1 nonmetal. They combine together. When you name them, so when you name ionic compounds, you name the metal, you add Roman numerals, if not groups, why did I put the comma? 1, 2, and some 13. So if you look at group 13, most of them are +3 in group 13, but one of them isn't. The chances you will see this is pretty rare. So you add the Roman numerals, and I'll go over what that means in a sec. If not groups 1, 2, most of 13, AG, CD, or ZN. Those are other big ones where you do not need Roman numerals. And I'll say why, and again, in a minute. So you just name the metal, sodium, zinc, iron. Put Roman numerals in parentheses if necessary. I'll go over what that means. And then, for the nonmetal, if it's from the people, you will change the ending to "ide." If you identify it's from table E, keep name the same. So whatever it is on table E is its name. So let's do a lot of examples here so you can see what I mean. Na2O. I see 1 metal. I see 1 nonmetal. This is binary, meaning there is only 2 total atoms, 2 total different atoms. There's 3 atoms total because there's 2 sodiums, but I only see 2 different ones. So, Na is sodium. Since sodium is in group 1, its charge is always +1. Its oxidation state is always +1. You will never have to indicate sodium's charge in the parentheses because it's always +1. So from here, just say what O is, which is oxygen, but change the last name to ide, sodium oxide. What if we had Fe2O3? If you look at iron on the periodic table, and you've been doing this a lot, very much so, a lot recently with the redox unit, you'll notice that iron can be +2 or +3, which means you need to figure out what iron's charge is. And you can do that by looking at the charge of the nonmetal. So oxygen is always -2, which means when we go look at our formula, oxygen is always -2. Since there's 3 of them, oxygen's total charge is -6. All 3 oxygens, you can write it like this if you'd like, will add up for a total of -6. These compounds, these charges need to add up to 0. So iron's charge must be something that allows it to be +6 to cancel out oxygen's -6. And since I have 2 irons, the only way that's possible, and if we check the reference table for iron's charges, is if it's +3. Because 2 times 3 is +6. 6 minus 6 is 0. So, naming it, we have iron. Indicate the charge in parentheses, 3 oxide. So you only need to put this Roman numerals if the metal, iron, has more than one option for a charge. Let's do a few more, and then we'll do molecular compounds. Let's do nickel fluoride. Okay, NiF2. Let's find nickel on the periodic table. Nickel has 2 choices for charges. So we have to figure out which one it is. Fluorine is only -1. Now, when you have a metal with a nonmetal, because I know some of you are going to start thinking, hey, what charge do I pick for the nonmetal if there's more than one charge? Usually, you pick the top one, since that's the -1, because when a metal bonds with a nonmetal, you need to make sure the nonmetal is always negative. So, always make sure the nonmetal is negative in an ionic compound. Okay, so we know fluorine is -1, and there's 2 of them, so that's a total of -2. We know this needs to equal 0 when we add them together. The only way that's possible is if nickel is +2. These cancel out. So we have nickel 2 fluoride. Change the ending to ide. So let's say it was chlorine. You had chromium chloride. Since chromium is our metal, chromium's only option is to be positive. These metals can never be negative. So when you pick chlorine's charge, pick the only negative charge it has, -1, because the metal must always be positive. So chlorine's -1, 6 of them make it a total of -6. To cancel out that -6, I need my 1 chromium to be positive 6. Chromium, 6 chloride. Now, what if they look something like this? CaCO3. If you have one metal but multiple nonmetals, multiple different nonmetals, so I see 2 nonmetals in this formula, carbon and oxygen. This, once you've identified there's more than one different nonmetal, had to have come from table E. You don't have any other choice. So, let's look up what CO3 is on table E. CO3 is carbonate. And when you look at carbonate, make sure you put it in parentheses and leave the charge on the outside. I would actually highly recommend you put all of table E in parentheses with the charge on the outside, because this is a table of ions, which means these are charged as an entire compound. So carbonate here is -2. All of carbonate is charged -2, not just the oxygen. Now in this particular example, oxygen also happens to be -2 because that's the only possible charge for oxygen. But if you were to take cyanide and you look at N, N has a lot of options for charges. That negative symbol is not applying to the N. It's applying to the entire compound as a whole. It's a CN, not N. So, we know carbonate as a whole, I've boxed it in so I don't make a mistake, is -2, which means calcium, and if you check it on the periodic table, must be +2 to cancel it out. This is calcium carbonate. Whoa, 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 Mr. G, why didn't you put calcium 2 carbonate? You can do that. You're not wrong. You're just being redundant. You're repeating yourself, because calcium can only ever be +2. Calcium has no other option but to be +2. So you don't have to tell me it's calcium 2, because that's the only option. All right, let's do another one with table E. Let's do, what do I want to do? I mean, this would be pretty easy to think off the top of my head, but sometimes you just never know. Let's do iron sulfate, FeSO4. So, I've identified that I have more than one different nonmetal. SO4 must have come from table E. When you go to table E, SO4's charge is -2. So, since I know sulfate is -2, iron must be, you guessed it, +2. Iron to sulfate. Now, what if we're working backwards here? What if we're given a name and we need to get a formula? Or what if we're given a couple of ions and atoms and we combine them to make a new formula? How do we make formulas with ionic compounds? So let's say you were asked to combine calcium and fluorine. You need to go to the periodic table and you need to look up each of their charges, because we have a metal and a nonmetal, which means it is ionic, which means it's bonded by that positive and negative attraction. So once you know you have a metal and a nonmetal, you know that you have an ionic compound, which means one is positive and the other one is negative. And 9 times out of 10, take the number only, and crisscross it down. CAF2. You can do the same thing with table E. If you were given iron 3 sulfate, iron 3 is Fe3+. Sulfate, if it ends in Te, it must have come from table E. Sulfate, in parentheses, is -2 as a whole. To balance those, take the numbers and crisscross them going down. What if you had, let's do a couple more. You were asked to combine, you were making a formula, and you pulled out these oxidation states, and you had zinc bonding with a phosphorus. Take your numbers and crisscross them going down. So these little numbers here, these are called subscripts. And they tell you how many of that individual atom you have. So this formula has 3 zincs and 2 phosphoruses. If you were doing something like, let's say, sodium phosphate, you know you need to go to table E, because this ends in Te, to get its formula. Put it in parentheses just in case so you don't make a silly mistake. Sodium is Na, and you know, if you're ever on the Regents, you know, our Regents is June 20th. A lot of you have already taken 3, maybe even 4 Regents prior. And it's the last one. You're tired. Summer is so close, you can feel it. And you get to a question, you're like, goodness, I don't even remember what the atomic symbol for sodium is. Go to table S and just find it. The symbols are all there with what they are. If you find yourself panicking, take a deep breath. You're going to be okay. And just find it on table S. It'll take time, but you know what? You got like 3 hours to take this test. You should have plenty of time. You should have plenty of time. So back to the problem. Sodium, if you look it up on the periodic table, has a charge of 1. Crisscross these down, and you get Na3PO4. You can leave this in parentheses if you want. That's okay. It's up to you. Now, if you had a formula, let's say it was iron 2 nitrate. This is nitrate. Nitrate has 1 N and 3 O's. If you have 2 nitrates, you have 2 nitrates. So this right here is like saying you have 2 of them. You have 2 NO3s. So you can think of like distributing this 2 and saying, oh, now I have 2 N's and 6 O's, which should make sense because you have 2 nitrates. So if you were to add these together, you would say, oh, I have 2 N's and 6 O's. And we'll go over a lot of these again later. But that is how you formula write and name ionic compounds. I will put a bunch of examples on my teacher site tomorrow. I didn't put examples from my teacher site for yesterday yet, because for some reason these YouTube videos have been loading very weird. So I want to make sure they're okay before I do anything. All right, let's name and formula write covalent/molecular compounds, and then I'm going to bed. What are you doing? Were you trying to like not be in the video?
No, I was in the video.
Oh, okay.
I went in the background.
You're silly. Molecular / covalent compounds. These are two or more nonmetals. Now the convention here, no Roman numerals, no checking of charges. Usually with your nonmetals, you use the Greek prefixes. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. So they're unbelievably similar to Table O, except 2, 3, and 4. 1, 2, 3, and 4 are all different. The rest of them should be the same. So, when you're naming a molecular formula, let's say, and I'm just going to make these up. Some of these compounds might not exist, but I'm just making them up for practice. S2P5. 2 means di. So the first one, you leave the name the same. Disulfur. The second one is when you change it to ide. Pentaphosphide. So not pentaphosphorus, pentaphosphide. That is disulfur, pentaphosphide. And the reverse is also true. Let's say you had triboron, like I said, I'm making these up, heptachloride. This probably does not exist, but we can make pretend. Boron is tri is 3, chloride is Cl, hepta is 7. B3Cl7. B3Cl7. Now, what if we had something like CO2, which in the back of your head, you probably know what that is. But if the first element is alone, you do not say monocarbon. When the first element's alone, just name the element. Carbon. Dioxide. But if the second element is alone, dihydrogen, you do use mono, monoxide. All right, so we'll do one more. No, we did S already. I'm tired of you, S. P4 BR I don't know. What do I want? 3. Fun. Tetraphosphorus. 4 means tetra. Tetraphosphorus. 3 means tri, like a triangle. Tri. Br is bromide. Yeah, and that's naming and formula writing. Check if it's ionic. I did a lot more ionics because we forget to check our charges. Stop doing that. And that's it. So you can kind of fast forward and rewind and play and pause and look through whatever you need to look through. But I think that's a good place to end it for tonight. Thank you for tuning in. If you have tuned in, these will be on my teacher site tomorrow. Have a good night.